Let us find the Frobenius series solutions of the equation x y2 dash minus y dash plus 4x cube y equal to 0. Here we are interested in finding power series solutions about origin. That is, we will be trying to find a solution of the form sigma aj x raised to j, or a solution of the form x raised to m into sigma aj x raised to j. That means we are interested in power series solutions which are expanded at the origin. So we are interested in finding the nature of origin x equal to 0, whether it is a singular point or an ordinary point, and if it is a regular singular point, it will have at least one Frobenius series solution. Now we will be transforming the given differential equation into its general form, which is of the form y2 dash plus p of x y dash plus q of x into y equal to 0. Here the given differential equation can be written as y2 dash minus 1 by x into y dash plus 4x square into y equal to 0. For the given equation, p of x is equal to minus 1 by x and q of x is 4x square. Hence, it is obvious that p of x is not defined at the origin. So, x equal to 0 is a singular point of the given differential equation. Now, to check whether this point origin is a regular singular point or not, we need to evaluate two more functions, x into p of x and x square into q of x. X into p of x is x into minus 1 by x, which is minus 1, and x square into q of x is 4x raised to 4. So, x into p of x is a constant function which is continuous. It is obviously differentiable at a neighborhood of origin. So, it is analytic at origin. Now, 4x raised to 4, it is a polynomial in x, and it is also differentiable around origin. So, these two are, that is x into p of x and x square into q of x, are analytic at origin. Hence, x equal to 0 is a regular singular point. Now, since x equal to 0 is a regular singular point, we can make a guess for the solution in the form x raised to m into sigma j varying from 0 to infinity aj x raised to j, where m is the root of initial equation. We know that the initial equation is given by m into m minus 1 plus m p naught plus q naught equal to 0, where p naught is the value of x into p of x at origin, which is equal to minus 1, and q naught is the value of x square into q of x at origin, which will be equal to 4 into 0 raised to 4, which is 0 itself. Hence, the initial equation will be m into m minus 1 minus m equal to 0, which can be expressed as m square minus 2m equal to 0. Therefore, m into m minus 2 is equal to 0, and this gives the roots 0 and 2. So, the roots of the initial equation are 0 and 2. When m is equal to 0, we try the solution y equal to x raised to m, that is x raised to 0 into sigma aj x raised to j, where j varies from 0 to infinity, which is summation over j varying from 0 to infinity aj x raised to j, and hence its derivative will be summation over j varying from 0 to infinity aj into derivative of x raised to j is j into x raised to j minus 1, and second order derivative is y2 dash equal to summation over j varying from 0 to infinity j into the derivative of x raised to j minus 1 will be j minus 1 into x raised to j minus 2, j into j minus 1 into, there is the coefficient aj into x raised to j minus 2. Now we substitute these power series into the given differential equation. We have xy2 dash minus y dash plus 4x cube y equal to 0. Substituting their power series, we have x into y2 dash will be equal to the series summation j varying from 0 to infinity j into j minus 1 into aj into this x raised to j minus 2 into this coefficient x will give x raised to j minus 1 minus y dash. Y dash is the series summation over j varying from 0 to infinity aj into j into x raised to j minus 1 plus 4x cube into y, that is plus 4 into x cube into y is the series summation over j varying from 0 to infinity aj into x raised to j into x cube, that will be x raised to j plus 3. This will be equal to 0 since we assumed that y is a solution of the given differential equation. Now we need to equate the coefficients of x raised to 0, x raised to 1, x square and so on. In general, we need to equate the coefficient of x raised to j to the coefficient of x raised to j on the RHS, which is 0. Before that, it will be convenient if we can transform these series such that the general term is the same for all these series. Here we can observe that the first series contains the general term x raised to j minus 1. In the second series also, the general term is x raised to j minus 1. Whereas in the third series, the general term consists of x raised to j plus 3. To transform the third series so that the general term contains x raised to j minus 1, we can apply the transformation I equal to j plus 4, so that j is equal to I minus 4, j plus 3 will be equal to I minus 1, and when j is equal to 0, I will be equal to 4. Hence, the series sigma 0 to infinity aj x raised to j plus 3 can be transformed as summation over I varying from 4 to infinity a I minus 4 x raised to I minus 1. Here the variable of summation is I, whereas in the first and second series of our equation, the variable of summation is j. So for better comparison, let us change the variable of summation back to j. Then we get the transformation of the third series as summation over j varying from 4 to infinity a j minus 4 x raised to j minus 1. Now let us equate the coefficients of x raised to j minus 1 on both sides. But before that, we can observe that in the first series j varies from 0 to infinity. In the second series also j varies from 0 to infinity, whereas the third series j varies from 4 to infinity. Hence, when we equate the coefficients of x raised to 0, that is the constant term, then the coefficient of x raised to 1, coefficient of x square and coefficient of x cube on both sides. We need not consider the third series. So let us first consider the term corresponding to j equal to 0. If we equate the coefficient of x raised to j minus 1, when j is equal to 0, we have 0 into 0 minus 1 into a naught, which is 0 itself, minus 0 into a naught, which is also 0, equal to 0. Now when j is equal to 1, the coefficient of x raised to j minus 1 in the first series will be 1 into 1 minus 1 into a1, that is 0, minus j equal to 1 corresponds to the coefficient 1 into a1 equal to 0 gives a1 equal to 0. Now for j equal to 2, the coefficient is 2 into 2 minus 1 into a2 minus 2 into a2 equal to 0. So this doesn't give any information about a2. Therefore, we can treat a2 as an arbitrary constant. Similarly, j equal to 0, when we equated the coefficients corresponding to j equal to 0, we didn't get any information about a naught. So we treat a naught as an arbitrary constant. Now j equal to 3 gives the coefficient 3 into 2 into a3 minus 3a3 equal to 0, which implies that 3a3 is equal to 0 or a3 is also equal to 0. Now for j equal to 4 and for higher values of j, that is when j greater than or equal to 4, we can combine the coefficients of x raised to j minus 1 from equation 2 to get the new relation j into j minus 1 into aj, that is the coefficient of x raised to j minus 1 in the first series, minus the coefficient in the second series is j into aj, plus coefficient of x raised to j minus 1 in the third series is 4 into aj minus 4 equal to 0. Here we can take j common to the first and second terms. Then we get j into j minus 1 minus 1, which is j minus 2 into aj plus 4 aj minus 4 equal to 0, which gives the recurrence relation aj equal to minus 4 aj minus 4 divided by j into j minus 2. Therefore, a4 will be equal to, that is when we put j equal to 4 in the recurrence relation, we get minus 4 a naught divided by 4 into 4 minus 2, and this can be expressed as minus a naught divided by 2 or 2 factorial. Now putting j equal to 5, we get a5 equals minus 4 a1 divided by 5 into 3, which is equal to 0 since a1 is equal to 0. Now a6 is obtained as minus 4 a2 divided by 6 into 4. We can cancel this 4 in the numerator and denominator to obtain the relation minus a2 divided by 6, which can also be expressed as minus a2 divided by 3 factorial. Now we can observe some pattern over here. Since a1 is equal to 0, we observed that a5 is also equal to 0, and we can observe from the recurrence relation that we can express A9 as minus 4A5 divided by a constant. So since A5 is equal to 0, A9 will be 0. So we can see that A8 is in fact plus A0 divided by 4 factorial. Similarly, we can find A10 as A2 divided by 5 factorial. So the solution will be y equal to sigma j varying from 0 to infinity aj x raised to j, and that will be equal to A0 plus, since A1 is 0, A1x is 0, A2 x square plus A3 is 0. So next term will be A4x raised to 4. A4 is in fact minus A0 by 2 factorial into x raised to 4 plus A6 is minus A2 by 3 factorial into x raised to 6 plus A8. A8 is A0 by 4 factorial into x raised to 8. Next is A10. A10 is A2 by 5 factorial into x raised to 10 plus etc. Now we can group those terms containing A0 together. So we get A0 into 1 minus x raised to 4 by 2 factorial, which can be expressed as x square whole square by 2 factorial. Next term containing A0 is this one. Here, after taking A0 common, we have the term x raised to 8 by 4 factorial, which can be expressed as x square whole raised to 4 divided by 4 factorial plus etc. Plus, now let us group those terms containing A2 together, which will give A2 into x square. Next term containing A2 is this. So we have minus x raised to 6 by 3 factorial, which can be expressed as x square whole cube by 3 factorial. Next term is x raised to 10 by 5 factorial plus x raised to 10 can be expressed as x square whole raised to 5 by 5 factorial plus etc. Now we know that similar series in the form 1 minus say t square by 2 factorial plus t raised to 4 by 4 factorial minus etc. This is in fact the series of cos t, and the series t minus t cube by 3 factorial plus t raised to 5 by 5 factorial etc. is in fact the series expansion of sin t. Hence, we can express our solution as A0 into cos x square. Here, instead of t, we have x square plus A2 into sin x square. Thus, we have expressed our solution as a linear combination of the two functions cos x square and sin x square. Here A0 and A2, the coefficients of these functions are arbitrary constants. Thus, this is in fact a general solution of our differential equation, and cosine function and sine function are mutually independent as well. Thus, we have obtained cos x square and sin x square as the independent Frobenius series solutions. These two functions give the independent Frobenius series solutions to our differential equation.